Hello, my name is Marcos and I will present this study titled Structures Discovering for Optimizing External Clustering Validation Metrics. This work was divided in 5 topics. The introduction presents the clustering and our objectives. Clustering optimization describes the proposed method. The dataset introduces the tested data. The experiments and results explain the tests to validate this proposal and analyze the clustering methods to compare this approach with state-of-the-art ensembles. And finally, we present our conclusions and future works. Clustering is a set of unsupervised machine learning techniques applied to extract information through the data patterns. The problem is to recognize these patterns correctly without human knowledge, using the spatial distribution to provide data ranges to be observed by specialists. Then, some validation metrics are applied to evaluate the cluster's quality. The measures observe the cluster's entities' behavior, such as centroid separation, average similarity, and the cluster's overlap indexes to select the best results. Thus, the objective is to evaluate these entities to optimize the clustering hyperparameters, striving for the best solutions to adequately separate the data. Therefore, the clustering expectations usually don't refer to features information, but implicit within theirs. This includes generate groups equivalent to classes in categorical tasks, or maximize the information acquired inside the subsets. To recognize the class entitlement, we experiment 5 internal validation indexes: silhouette score, Kalinske-Harbauer score, Davis-Boulding score, mean cluster size, and mean cluster similarities. To evaluate the solution's quality, we analyze the external validation indexes: adjust branding index, normalized mutual information, and clustering accuracy. Evaluating the internal indexes, we aim to optimize clustering parameters and consequently recognize appropriate cluster solutions on external indexes. The clustering process includes test multiple parameters. They are specific for the selected algorithm in addition to the traditional number of clusters or affinity distance. However, the idea is overpass the exhaustive search and the use of elbow method specialist observation costs. Selecting automatically these parameters, we expect to suppress partially the specialist work and define the best clustering groups, reducing the annotation efforts. The state-of-the-art methods on clustering for categorical data are ensembles, applied to recognize the data geometries among the algorithm's calibration. Besides that, traditional clustering algorithms are simple and versatile to be applied in some tasks to assess the ensemble gain. The traditional algorithms are independent procedures, while ensembles are high clustering methods that include merging multiple clustering tests. The merging produces the consensus knowledge, the result of more robust hyperplanes to represent the data through multiple decision zones. However, the clustering optimization evaluates the hyperparameters on clustering process to designate an optimized result. The example of the R15 dataset above presents some tests using multiple metrics. The ensemble methods combine these tests in a consensus merge procedure, while the traditional optimization technique tune the parameters to select the best result using the internal indexes. Furthermore, our proposal discusses reinforce the traditional methods, evaluating the algorithm's partitioning behavior to achieve results compatible with state-of-the-art ensembles. The experiments observe the agglomerative clustering empowering its potential by tuning the hyperparameters. The clustering test reduction is analyzed according to the influence of 3 optimizers: dummy, a simple random uniform sampling method; forest, a decision tree sequential optimizer; and Gaussian process, using a Bayesian optimization according to the normal distribution. The clustering entities are observed within the objective function as an internal indexes optimization. The external indexes indicate the results quality. This figure presents an example of clustering optimization using R15 synthetic dataset through the silhouette coefficient. Using this, the optimization evaluates overlapping separability and nested samples to adapt the algorithm for most adequate results. To test this method, 3 dataset models are evaluated: synthetic, usually containing 2 or 3D samples that challenge clustering to separated nested groups; categorical, collected from UCI repository, expecting to reduce the classification effort, reproducing the categorical zones, extracting information indices and class clusters relations; and textual, categorical, high-dimensional data, confusing for unsupervised learning through a few representative features aligned to the class information; and textual, categorical, high-dimensional data, confusing for unsupervised learning through a few representative features aligned to the class information. Textual data are a hardware test for correctly partitioning. The first experiment evaluates the optimizer impact on clustering cycles reduction during the hyperparameter study. The results include the Gaussian process with a 58 less clustering cycles followed by Forest 56 and Dummy 51 gain. This difference means a reduction of 14,000 clustering tests, less than exhaustive search. Important to highlight the increased difference between the optimizers applied on datasets with more samples that dynamically modify the clustering test range. The experiments test parameters combinations to fit the clusters on identifying data alignment and partitions, which indicates more consistent clusters in similar and separated data. The figures present the results of synthetic data processing with performance changes under a distance metric perspective for external indexes. In these examples, the dataset shapes and complexity modify the chart perspective according to the sample's affinity. In this point of view, the metric choice impacts on dataset clustering performance beyond the number of clusters, indicating a good solution for information retrieval, clustering arrangement, and class assignment. When optimized, the hyperparameters combined can almost partially reproduce the ensemble effect, drawing robust clusters delimiters to recognize the data geometry. The categorical and textual datasets highlight this nuance, indicating the cluster class alignment, feature relevance, and optimization gain. In an overall observation, mixing both areas became measurable the categorization complexity and how it can be solved by clustering. The results achieved using the optimization are equivalent to ensemble techniques. In a total of 16 datasets, our model presents improvements in 27 measures encompassing 15 of these datasets, with at least one measure increase. We select 4 datasets: Balance Scale, Breast Cancer Viscosity, BaseHawk, and PCMAC to present summary results. Balance Scale with a CA 4% better than ensembles indicates that single algorithms solve adequately the clustering partitioning for class alignment better than ensembles, while Breast Cancer Viscosity has the opposite behavior. Besides that, BaseHawk and PCMAC textual datasets demonstrate this method as a powerful model with great advantages on ensemble methods. Thus, the experiments result in enhancements of 67 of total datasets in the adjusted random index, 81 in normalized motor information, and 50% in clustering accuracy. As conclusions, in this study, we observed the optimization using internal index impacts directly on external indices quality. and each parameter set can be observed for an individual external validation. The geometrical identification works on fine-tuning perspective according to the class environment and clusters partition. Furthermore, optimizer clustering algorithms reproduce the good results of state-of-the-art ensembles and can be adopted as an efficient method for several datasets. As Future works, we test ensembles merge procedures before the clustering optimization methods to acquire most valuable knowledge. This method has a potential performance gain mixing both approaches to generate more robust decision zones. And finally, we expect to test this method as a classification sampling to increase the categorization performance on reducing the specialist effort, testing on other tasks such as natural language processing. Thank you for watching. For suggestions or any question about this work, please email me.